No, what did she get into at school? Oh, really? Oh, wow. Oh, that's a congrats.
Okay, once again, good evening, folks. And this is Professor Ayorinde, welcoming you to another session of organic chemistry. When we left on Tuesday, we were discussing the infrared spectroscopy. Today we are going to continue our discussion of spectroscopic methods. And for today's discussion, we are going to discuss the nuclear magnetic resonance spectroscopy. For nuclear magnetic resonance spectroscopy, we will be looking at light energy within the radio frequency region, which is a fairly low wavelength, very low energy region of the electromagnetic spectrum. But before we start this discussion today, I do have a few announcements. I want to remind you that on Monday, we are going to have the online session at 8 p.m. I will email you to remind you. For that session, we are going to use the chapter 13 end of chapter problem in R for the online review session on Monday. Also, I do want to also let you know that I'm sure you already know that I sent out the two surveys, information about two surveys that you need to complete. The one survey from the College of Arts and Sciences, you need to complete that, and when you finish that survey, make sure you can give me the confirmation page so I have to give you the appropriate credit for that. And then the other survey is the one on Survey Monkey. So go ahead and complete that. The due date for that is tomorrow, which is Friday, so 11 p.m. tomorrow. So make sure that you complete that survey by tomorrow, so you get the credit also.
With those surveys, instead of it going under participation,
yes, yes.
That would be more helpful.
So they want to make up a new syllabus. next semester, Tony, I will call you when I want to make up that syllabus, so we'll make it up together.
No, I don't want to do the next.
Okay. Anyway, so let's get going here. We're going to start with the nuclear magnetic resonance spectroscopy, and as I told you, the energy that is involved in this spectroscopic method is derived from the radio frequency region of the electromagnetic spectrum, which is this right here. Okay, nuclear magnetic resonance spectroscopy. The question now is, how do we define this? I'm going to take you to this slide. I hope you guys can read it. I know, Jessica, I know you've got very good eyes. Can you read this for us, this right here?
The absorption of light energy in the radio frequency range by steady nuclei under the influence of external magnetic field is known as nuclear magnetic resonance spectroscopy.
Okay. There you go. That is the definition of nuclear magnetic resonance spectroscopy. This slide is actually taken from the book that I wrote in 1982, before all of you were born. So I wrote that book in 1982, so I thought maybe some of the material that we use in this course actually still taken from that book. So anyway, that is the definition of NMR, which is a nuclear magnetic resonance spectroscopy, which is the absorption of light energy in the radio frequency region. And in this particular instance, we are going to be looking at the nuclei of hydrogen, which we refer to as the proton, and also carbon-13. Okay, so those are the two nuclei we are going to be looking at for this particular discussion. Now, ordinarily, when you have there are certain types of atomic nuclei, for example, like the proton, carbon-13, fluorine-19, phosphorus-31. Some of these nuclei behave like a spinning magnet. You know what a magnet looks like? They behave like a spinning magnet. But for our discussion, we are going to focus our attention only to the nuclei of the hydrogen atom, which we refer to as proton, and then the carbon-13 nuclei. Okay. Under the normal circumstances, these nuclei, when they are just placed within themselves without the external magnet, you find that they are spin, they are oriented in just random direction. So look at this, think of this here as nuclei of either carbon-13 or hydrogen or the proton. You see the orientation is just randomly directed. But as soon as you place an external magnet here, you place an external magnet within the vicinity of this nucleus, spinning nuclei, then they begin to assume specific orientation. In which case, you see here, some of these nuclei are aligned, they are spin aligned, the spin is aligned parallel to the magnetic field of the external magnet. And on the other hand, this here, they are spinning opposite to the field of the external magnet. In other words, they are simply aligned in the opposite direction. So in that case, what you have here, you almost think of somebody's. You have a river, somebody swimming with the current, and then another person decides to swim against the current. Who is going to expend more energy? The one swimming against the current. So you're going to have two energy levels. And that is what we have here. So under the influence of an external magnet, the spinning nuclei, they assume two energy levels. And those two energy levels we call the higher energy state, we call the beta spin state. And the lower energy level we refer to as the alpha spin state. Okay, this is your magnet here. You're varying the strength of your magnet. The greater the strength of the magnetic field, you could see the delta E, in other words, the differential between the lower energy level, which is the alpha spin state, and the upper energy level, the beta spin state. The greater the external magnetic field, the greater that delta E will be. In other words, the differential in energy between those two spin states. Now, the absorption of light energy by the nuclei that are in the alpha spin state, right here, to go from here to here, the absorption of energy is what we measure under nuclear magnetic resonance spectroscopy. By the way, this is the same technique that is used for your magnetic, what is it, MRI, magnetic imaging.
Resonance.
Yeah, magnetic resonance imaging. Yeah, thank you. Now, it used to be called nuclear magnetic resonance imaging, but because a lot of people were scared of the word nuclear, that is why they take the nuclear out of it. So now you go to the hospital today and say MRI. It's the same principle that is being used here. Okay, anyway. So here, what are we interested in? The basic principle behind NMR is the absorption of light energy by protons or carbon-13 or by spinning nuclei that are in the alpha spin state to go to the beta spin state. This process we call flipping. In other words, we say that the nuclei are flipping. Okay? They're flipping from one spin state to another spin state. So we therefore say that both of them are in resonance. We say they are in resonance. Going from the alpha to the beta. And that is the underlying principle of everything we do with regard to nuclear magnetic resonance spectroscopy, which is essentially the absorption of light energy within the radio frequency region from this alpha state to the beta state. And now, how does that apply? How do we use it as chemists? The question is, how do we find it useful? Okay. Now, this absorption of energy I find my pen. This absorption of energy we refer to as chemical shift. Okay, that is the resonance from the alpha spin state to the beta spin state. We call that chemical shift. That is the absorption of energy, and that's what we measure. Now, say for example, if we take a look at this molecule, let us take a look at this molecule. How will this absorption of energy, how will it help us? How will chemical shift help us to determine the structure of an unknown molecule? Remember here that what we have, we place the nuclei in the vicinity of an external magnet. What is going to happen, if you look at this hydrogen here, that is attached to this carbon, that carbon is attached to oxygen. We know that oxygen is electronegative, right? We know that, right? Now, what is going to happen, because oxygen is electronegative, it is drawing electron away from this carbon here, and also drawing the electron away from this hydrogen attached to that carbon. What that means is the nuclei of this hydrogen will be more exposed to the effect or to the impact of the external magnetic field. So therefore, what you're going to find here is that the chemical shift of the hydrogen attached to this carbon will be greater than the chemical shift attached to this carbon, because there is what we call the shielding. Because this nuclei here, they are not as shielded with the electronic cloud as much as this is and as much as this is. Okay? Because the basis of the NMR spectroscopy is that we are exposing them to external magnetic fields. So the more exposure they get, the greater the chemical shift is. You follow that? Okay, so therefore, I will expect the chemical shift of this hydrogen here to be greater than the chemical shift of this hydrogen, and the chemical shift of this will be greater than the chemical shift of this hydrogen. So you begin to see how we can do this. So all that we need to know is to know the various chemical shifts for different types of hydrogens. And by the way, what I'm telling you now about the hydrogen or the proton also applies to carbon-13 nuclei. Okay, so that is one where we actually begin to see the importance of the chemical shift. Now, before we move forward, since what we do is to measure the various chemical shifts of different protons or carbon-13, what we do, we have what we call a reference standard. And for that reference standard, we use this molecule here. This we call tetramethylsilane. Tetramethylsilane, and this is abbreviated as TMS. So you're going to hear us say TMS quite often. TMS. Now, we use tetramethylsilane as a reference standard for all chemical shifts, because if you look at this molecule here, by experiment, we know that the chemical shift of the hydrogens in this molecule is much lower than the chemical shift of most hydrogens in organic molecules. So therefore, we arbitrarily assign a value of 0. Chemical shift of this as 0. So we assign TMS an arbitrary value of 0. And therefore, we reference all other chemical shifts to the TMS signal. And by the way, the unit of measurement for chemical shift in the radio frequency region is cycles per second. Unit of measurement is cycles per second. Which is we call Hertz, and the symbol for Hertz is Hz. Okay, I'm sure you read it, listening to radio stations say 20 megahertz and all that kind of stuff. That's essentially what it's saying. Now, so that is the unit of measurement. Now, there's another aspect to the NMR spectroscopy that also I want you to know before we move forward. Okay, at this point we know we use our TMS as the reference standard. Okay. Now what happens in reality, you do have a lot of commercial spectrometers that are commercially available for us to use in the NMR experiments. And these spectrometers, they come with different, what we call different frequency strength. So in practice, what we normally do, for most of the instruments that are out there, you have an external magnet, and then what you do, you scan the radio frequency to the sample of interest. Okay? And since you want to keep the external magnet constant, you're scanning the radio frequency constant, you're scanning the radio frequency through the sample, and then you simply measure the chemical shift at which, of course, the proton or the carbon-13 will flip from one the alpha spin state to beta spin state. Now, let me give you the series of instruments that are now available. You have a series of instruments out there. Available instruments. With different frequency, in other words, energy. Very often we have what we call a 60 megahertz instrument. We have the 100 megahertz instrument, the 200 megahertz instrument, a 300. One of these days when you have the time, you come to my office, I will show you. We do have the 300 megahertz instrument downstairs and also 400 megahertz instrument. And so on and so forth, 500. Why do I bring this up? Huh? Why do I bring this up? Every time you use any or each one of these instruments, since their strength is different, the chemical shift will be different for a particular process. Say for example, let me go to a blank page. Let us say we have, remember we told you that we use the TMS as reference standard. The TMS is here. Okay, say 0. And the unit of measurement we say is Hertz. Let us say we have some kind of proton that has an absorption at 400 Hertz. Using a 200 megahertz instrument. Okay. If you use another instrument, this chemical shift in Hertz will be different. So therefore, how do we normalize this? For example, you do your experiment in your lab, I do mine in my lab using different instruments. How do we normalize this so that if I say I have a particular absorption in my lab, you know exactly what that means. So to do that, we have a universal chemical shift scale. Universal chemical shift scale. And what is that scale? We use that scale, we call it delta. With the Greek symbol delta. And the mathematical expression for delta equals to chemical shift. Let me use a different pen so we can see that better. Because chemical shift which is in Hertz, which is cycles per second, divided by the frequency of the instrument, the spectrometer's frequency. By the way, when we say 200 megahertz, this mega here actually means million, not thousand, means million. Okay? So therefore, the chemical shift, the universal chemical shift is expressed as delta, and the mathematical expression for delta is chemical shift in Hertz divided by the spectrometer frequency. So in this case, what would be the chemical shift in delta for this hydrogen if we say that it has an absorption at 400 Hertz and the strength of the instrument is 200 megahertz? What would be the chemical shift? Can anybody work that out for us? That would be what? That would be 400, right? Hertz divided by 200 megahertz, right? What would that be? What is it? Is it just 2? Are you sure? Don't forget the unit of measurement now. Okay. Okay, so you so you cancel out the hertz, right? That cancels out, right? So that becomes 2 over m. And what is m? We told you m is million, right? So since m is million, so this means 2 parts per million. So this therefore becomes 2 parts per million. So I will therefore express the chemical shift for whatever proton is given or the carbon that is giving this signal. I will say the chemical shift is 2 parts per million. So this mathematical expression is very important. If somebody asks you, you could be asked, for example, we could give you the chemical shift in parts per million and say determine the strength of the frequency and the spectrometer frequency that was used to collect that data. So what do you use? Then you use this expression here. So you could have 3 different unknowns. You could be given the chemical shift in parts per million, given the absorption in hertz, and we could tell you to give us the spectrometer frequency, or we could give you the spectrometer frequency, give you the parts per million, and tell you to determine the absorption frequency in hertz. So anyway, that is very important. Some of when you get to use going to R, I will be asking you those kind of questions. Okay, so that is the equation that you need to use. Okay, so now let us get back to this here. So at this point, we begin to see the importance of the chemical shift. So if I ask you, what is chemical shift? What is chemical shift? Can you describe chemical shift for us? What is chemical shift? Anybody? Yes, David. How much? Okay, okay. The chemical shift is the absorption of energy to go from the alpha spin state to the beta spin state. Okay, and that chemical shift is specific to each proton or each nuclei has their own chemical shift because they are in different electronic environments. Why are they in different electronic environments? We told you earlier because of the fact that each one of them may be exposed to the external magnetic field to a greater extent. Say for example, I give you this here. Supposing I give you this. Based on what we know now, okay, which one of these hydrogen here or proton here will have the greatest chemical shift in this molecule? The one next to oxygen, exactly. So this one will have this here. I will expect the chemical shift of this hydrogen here to be greater than the chemical shift of this hydrogen. Okay, now will you expect the chemical shift of this to be different from the chemical shift of this? Yes. Because here, this methyl group is attached to the carbonyl group. And carbonyl is that carbonyl carbon is an sp2 carbon, which is electronegative. We pull the electron away from this hydrogen. That is how we begin to now use this to reconstruct the structure of unknown molecules by knowing the chemical shift. I'm sure you're sitting down there. How are you going to know all of this? Don't worry, we will give you the table of chemical shift. Okay? So I will email you. I will make up a table of chemical shift and email it to you. But if you want to make up your own table of chemical shift, you are free to do that. They are all available in your textbook. Okay. Okay, so now we know about chemical shift. We know the importance of chemical shift. Now, in addition to chemical shift, in order for us to now be able to use the NMR spectroscopy to determine the structure of unknown, we need 3 additional sets of information. And those sets of information is absorption signals, multiplicity, integration. We already know something about chemical shift. You know that is the absorption of radio frequency energy. And that each nuclear will have different chemical shifts because they are in different electronic environments. Is that correct? He's not listening to me. You are listening. Okay. Okay, now let us take a look at absorption signals. Okay. To get to absorption signals, let me give you a little background. Supposing I give you this molecule here. So now we want to deal with absorption signal. Supposing I give you that molecule. How many different types of hydrogen do you have in that molecule? 1. She never got it right. She said 1. Exactly. That is 1. All of this hydrogen in this molecule here, they are all in the same electronic environment. And as such, how many signals do you expect for this molecule? 1. 1 signal. So therefore, if I give you an NMR spectrum, what we call an NMR spectrum, something like this, you have the peaks shown like this. So those chemical shifts, the graphical representation of those chemical shifts is what we refer to as NMR spectrum. And just as in the case of the mass spectrum, we could also give you this data in a tabular form. Okay? Now, the question now is, supposing I give you an NMR or NMR spectrum, in this case, proton NMR spectrum, and that spectrum has 2 peaks. And I tell you that compound is a cyclohexane. Will you tell me that I'm correct or I'm wrong? Wrong. You tell me I'm a liar, right? that cannot be correct. Okay, these are the kind of things when you go to the court, because these are the type of instrument they use to solve cases. And then you become an expert witness. They bring you to the court and say they give you the spectrum. Does this look like the spectrum of the drug that this person has just taken? You say, of course, no, it doesn't look like the spectrum of any drug. Okay, and that person will then go free, right? Because the data doesn't match what they're supposed to be. Anyway, so in this case, we expect that the signal of this molecule should be only 1. Now, supposing I have this. Now, how many different types of hydrogen do you now have in this molecule? 2. Okay, let's see if you can label them. You say this is 1, and this will be the same as this, right? Yeah. Right? 2, and this is the same as this, right? You follow me now? Yeah. Okay, are you still saying 2? 3, exactly. So now we have 3 types of hydrogen. So how many signals do you expect in the proton NMR spectrum of this molecule? 3. Now you begin to see how simple this is. 3 signals.
I have 3.
Yes. As you have 3, this is one type of hydrogen. Because this hydrogen here and this hydrogen are equivalent. This is another type of hydrogen. You see it? And then this is the third type of hydrogen. Right? This here is one type. This is the second type. And this is the third type. This and this are equivalent. This and this are equivalent. And this is just by itself. So you're going to have 3 types of hydrogen here. So therefore, the first thing you look for, how many signals do you see? The number of signals you see tells you the number of different types of hydrogen or different types of carbon-13 you have in the molecule. Okay? The same thing we are saying with for the proton also applies to carbon-13 NMR. Now, supposing I have this. Still dealing with absorption signals. Supposing I have this. Supposing I have that, how many different types of hydrogen do I have in that molecule? 4. Okay, let's number them. Are you saying this? Let me use my color pen. This hydrogen here, they are equivalent, right? So that is one type. So that is one type. Which is the second type? This here, this hydrogen here. Everybody follow that? So that's 2. And that is 3. And this is 4. Okay? Now, if we now begin to look at the chemical shift, I will expect the chemical shift of this to be the highest, right? Followed by the chemical shift of this here. And then this will be, so in terms of chemical shift, I will expect this to be the greatest or most, let us say most, let's use the term most here. And then that will be greater than this one here. Okay, so this one I will say next, for lack of better word. Then I will say that is greater than this one here. I will say second next, right? Can I use second next? Okay, next 2. And then finally, the least chemical shift in this system will be what? This here. This here. So this will be next 3. So I will expect the chemical shift of this to be the highest, followed by the chemical shift of this, followed by the chemical shift of this, followed by the chemical shift of the metal. So now, giving you 2 features of the NMR spectroscopy, chemical shift and absorption signals. Now, what does absorption signal tell you? What does it tell you?
The number of different hydrogen.
The number of different types of hydrogen in the molecule. Or if you are dealing with carbon-13, the number of different types of carbon-13 or carbon you have in the molecule. Is that clear? Okay. So far we have now finished the 2 major features of the NMR spectroscopy. Once we finish all of the 4, then we'll begin to solve problems. Now let us now take a look at multiplicity. Multiplicity. That is very important. Multiplicity, what we sometimes refer to as spin spin coupling. What does that mean? What it essentially means is this nuclear, in the case of this, the proton or carbon, the nuclear of these atoms, they do interact with each other. If, for example, I have this molecule here, here I have that molecule. When it comes to the interaction of those hydrogens with each other, which we refer to as spin coupling, there is what we call the N+1 rule that will help you. N+1 rule. And what does the N+1 rule say? Now, listen very carefully now, because this is most important. I'm going to write it down so that you guys will not miss my action with what I am trying to tell you, because it's very, very important. Now you have the N+1 rule says the signal of a set of hydrogens, the signal of a set of hydrogens. When I say set of hydrogens, for example, this would be a set of hydrogens. Okay? This would be a set of hydrogens. This would be a set of hydrogens. So the signal of a set of hydrogens will be split. Into N+1 peaks, where N equals to the number of hydrogens that is on the adjacent carbon atom. N equals to number of hydrogens in the adjacent carbon atom. When we say adjacent carbon atom, what do we mean? Next carbon atom. So what are we saying here? So according to the N+1 rules, what we mean is the signal of this methyl group, this set of hydrogens, will be split into three, because this methyl group, these three hydrogens here, they are looking at only two hydrogens. Think of this as looking at, they see these two hydrogens. Similarly, these two hydrogens here, what do they see? They see this hydrogen. But this hydrogen here do not see this hydrogen. So therefore, what we say the multiplicity of this methyl group will be what we call, change the color of my pen, we call this a triplet. We call that a triplet. Okay? So we call that a triplet. You guys are laughing. Okay? Which is sometimes represented as a T, right? Triplet. Okay? Now, the multiplicity of this hydrogen here, keep in mind the multiplicity tells what is next to it. Okay? The multiplicity of this hydrogen here will be what? split into how many? 4. Because n is 3. N plus 1 is 4. So that would be a quartet. I will look like this. Call that quartet. Okay? And then sometimes we represent that as cube. It could also be a quintet. So if it is a quartet, make sure you write quartet because you don't want to mix quartet with quintet. Quintet means 5. Yes.
Could you explain that again? I'm sorry.
Okay.
Just the quartet part.
The quartet part. Okay.
Yeah.
You do understand the triplet part.
Yeah, because it's because the hydrogen has 3.
Because it is C2, therefore it must be split into 3, n plus 1. Okay, here the quartet, keep in mind n plus 1 row.
Right.
N is the number of hydrogen that this hydrogen will see.
Okay.
Okay, this hydrogen are seeing 3 hydrogens.
Oh. Okay.
Okay, because these hydrogens are seeing 3 hydrogens.
Yeah.
Then n 3 plus 1 is 4.
What do you use the other one?
What other one?
Hold on.
There's a rule we call n plus 1. Okay, n equals to the number of hydrogen that a given set of hydrogen will see. Okay, this hydrogen here is seeing only 3 hydrogens.
Yeah, it's like a dream.
Okay. Okay, so therefore, yes.
What's the importance of knowing that it's a triplet or a quartet?
Don't worry, we'll get there. We'll get there, okay?
We don't see.
We'll get there. Okay. Now, look at this here. What do you think the multiplicity of this will be? This hydrogen here. Singlet. Okay? So this will be a singlet. Because it is seeing no hydrogen. 0 plus 1 is what?
1.
Right? 0 plus 1 is 1. That's a singlet. So we call that S. Okay? So now we explain to you chemical shift. You know what chemical shift is? You know what absorption signal is, right? Now do you know what multiplicity is? Multiplicity is simply telling what is next to it, the neighbor. In other words, this is my neighbor here. Okay? Okay, I am CH2. This CH3 is my neighbor. That's what we say. So if I say I am quartet, that means a CH3 is next to me. Okay? Now, the last thing I want us to look at before we begin to solve problems. Now we've looked at all of this. The last thing we need to look at now is integration. Integration. Now, we know the multiplicity of this methyl group is triplet. The multiplicity of this methylene group is quartet. The multiplicity of this methyl group is singlet. We know that. Now, let us now look at integration. Now, what the integration will do, take this out of here. The instrument is designed to also measure the area under each signal to determine how many hydrogens are given those signals. In other words, the integration will tell you that here you have 3 hydrogens, you have 2 hydrogens, you have 3 hydrogens. That is what the integration will tell you. Sometimes you may need to do a little bit of measurement together, but most of the modern instruments today will actually do the measurement for you and tell you this is the number of hydrogen. So you begin to see the power, but of course we are going to use a combination of the old instrument and the new instrument. We like to do some measurement also. So you begin to see the power of the NMR spectroscopy. Now, let us now start doing some problems. Supposing I now give you Let's keep this here. Supposing I give you this, I'm trying to make up something here, right? Supposing I give you this, okay, and I ask you to give me the proton. I ask you to give me the proton NMR spectrum of this compound. What will it be? Okay, I will give you the chemical shift. Okay, the chemical shift of hydrogens of methyl group attached to carbonyl is somewhere between 1.8 and 2.5 parts per million. Okay, that much you know now, right? The chemical shift of a methyl group that is attached to a carbonyl is somewhere between 1.8 and 2.5. So, okay, I ask you to give me the PNMR data for this. The first question you're going to ask yourself is, how many signals are you going to see here? One. Only one signal. So, I say let's use a number, 2.2 parts per million. What will be the multiplicity? What will be the multiplicity? What is singlet? I said singlet. How many hydrogens? 6. Okay. Okay, very good. Supposing I take this off. I didn't tell you what the compound is. I did not tell you what the compound is, right? And I tell you, all I tell you here, let's see, let's add up something here. 30 plus 28, that's 58. Good. And I tell you that the mass spec data for this compound is at N over Z 58, and that is the molecular ion. And I tell you, this is the proton NMR spectrum, and I say, give me the structure of that molecule. What will you do? You are already giving it to you, but you begin to see what you can do here. So how are you going to approach it? You know the molecular weight is 58, right? You know this molecule contains only one type of hydrogen, and that one type of hydrogen is 6. So then what are you going to do? The chemical shift is 2.2. That's chemical shift not too far from a carbonyl. So in this, you have no choice but to say this molecule is this. So that is the only molecule or structure that will fit this molecular weight. Okay? Now, supposing I do this. Let's give you another example. Supposing I give you this molecule here, CH3, CH2, carbonyl, okay? What will be the proton NMR spectrum? And I ask you to give me the proton NMR spectrum of this compound. What will it look like? What is the first question you're going to ask yourself? How many different hydrogens do you have in this molecule? Now, if I was asking for carbon NMR, then you ask yourself, how many carbons, different types of carbon do you have in this molecule? Okay, so let us answer the first question. How many different types of hydrogen do we have in this molecule? 4. So you expect to see how many signals? 4. Exactly. You got plenty of time. Oh, plenty. You got plenty of time. Okay. So we have 4 signals here. Now, I will tell you now, the hydrogen attached to a carbon that is attached to an oxygen, the chemical shift is somewhere between about 2.8 and 4.5. Okay? So therefore, if you already know those, you see, I know you're supposed to know those too. Okay. So let us begin to now give you the proton NMR data for this. I will start with this here. Take my pen. This here I will say 3.5. This hydrogen here 3.5 parts per million. What would be the multiplicity? Quartet, exactly. That would be quartet. How many hydrogens? 2. About this here. About this here. Okay, I need some else now. About this. What would be the okay, the chemical shift of this here is not exactly attached to oxygen, would be somewhere between but not too far from it, about 1 to 1.5. Okay? So let's make it 1.2, right? Okay, 1.2. You see here, I'm just making this up, right? 1.2 is somewhere between, supposed to be somewhere between about this could be about 1.2 to about 1.7. So let's say 1.2 parts per million. Okay, what would be the multiplicity? Triplet. So we call it T. And how many hydrogens? 3. Okay, since now we've accounted for 4 signals. We have 2 more signals to go. About this here. Okay, this hydrogen not yet, just that. Oh, yeah, what is the, what would be the, well, you don't know the chemical shift for. Okay, let me give it to you. Chemical shift for this here, not too far, is next to carbonyl. Okay, somewhere between, you know, we could say about 1.9 to 2.5. So make it 2.2. No, generally these chemical sheets are range, you know, it's a range to them. So as long as you have some value within that range, that is fine. Okay, so that's 2.2 parts per million. What would be the multiplicity? 7. Very good. 7, because this is 6. Therefore, 6 plus 1 is 7. So that is septet. Septet. Because it is, this hydrogen here is seeing 6 equivalent hydrogen. So that is septet. And then the number of hydrogen is how many? 1. About this here. About this equivalent hydrogen here, the metal. The chemical shift, okay, let's say, generally that would be somewhere between 0.9 to 1.5. Yes.
Is the ppm given, or do you have to figure it out?
No, you will give you a table of ppm.
Oh.
Okay, but if you want to figure it out, that's fine.
No.
You can figure it out. You know, we will give you a table of parts per million, the chemical shift. Okay, so the parts per million, the chemical shift for this metal group here, you know, let's say 1.1. Okay, and what would be the multiplicity? Doublet, exactly. Why is it a doublet? Because they are seeing only 1. So doublet. And how many hydrogens? 6. So therefore, if I was supposed to give you this data, this is the way I will give it to you. I will say, I'll start from the lowest one, which is the, okay, 1.1. I'll say this is the PNMR data, proton NMR data. Okay, chemical shift in parts per million. Okay, 1.1, comma, doublet, 6 hydrogen. That is this here. Then I'll go to the next one. I say 1.2, triplet, 3 hydrogen. Then I will say I'll go to the next one, 2.2, right here. 2.2, septet, 1 hydrogen. And finally, I will give you 3.5, quartet, 2 hydrogen. That is the data I will give you. And of course, you will be given either the molecular weight or the molecular formula from the mass spectrometer. And then you will be told to provide the structure for the unknown. Yes?
Is it wrong if we, for the 2 metals, if we wrote them separate and said 3 hydrogens?
No, they are, because they are equivalent.
So you,
no.
you put them together?
They are one set of signals. Yes.
Okay.
Because they are equivalent. Okay. So now let us see. Now, so you begin to get the idea. Let's now go through this and do some problems. Okay, we've already gone through this. We told you about the internet standards, and we also gave you this the universal chemical shift scale, which is delta. Okay, so let us just go through this real quick. All of this we've done already. Now this is the TMS. With the signal for the TMS, we say it is upfield, and everything to the left of TMS, we say it is downfield. That's just some terminology that we use. Okay, and anything, the more shielded the nuclear, the more shielded the nuclear, the greater the chemical shift. Okay, in other words, when you have, the closer you have electronegative atoms next to a particular proton, the greater the chemical shift will be. Okay, now you begin to see the table of chemical shift. Okay, this is kind of, I'll put all this together. You know, all those numbers I was giving you, I was getting them from here. Okay, of course, that's the TMS. Okay, so we're going to send this to you. All of this, these are the table of chemical shift. Okay, now if you are dealing with carbon-13, also have similar table of chemical shift. With carbon-13, we go from TMS, as chemical shift parts per million, from 0 to about 220. You can see the range here. Okay, but we're going to talk about carbon-13 after we finish with the proton. Now you look at this molecule here. Look at this molecule here. How many signals do you see here? 2. Because you only have this and this. Okay, let me ask you, which of these signals belong to what? Let's call this A. Let's call this B. Which of these 2 signals belong to A? The one at 3.6. Okay. This is the actual data from the instrument. So that would belong. That would be the A, because A is next to oxygen, and therefore the one next to the carbonyl is about 2.0. I told you about generally range from 1.8 to 2.5. Okay, now let's take a look at this one here. Oh, this is carbon. This is carbon-13. Okay, this is the proton NMR. This is the carbon-13 NMR. In the carbon-13 NMR, you see here, just as in the proton, how many different types of carbon do you have here? 3. And that's what you see here. You have 1 type of carbon, another type of carbon, another type of carbon. And that is why you have 3 signals, 1, 2, and 3. The carbonyl carbon is generally in the range of 180 parts per million. So this is the carbonyl carbon, if you're looking at carbon. Okay? And then this is the methyl carbon, if you look at this here. That is the methyl carbon. And this is the carbon that is attached to oxygen. So the same principle that applies to hydrogen also applies to carbon. Okay, we've gone through all of this already. Okay, that's from my old book. You see the difference. In those days, we did not have, that was before the internet and the word processor and all those kind of, so you have to type out everything. Okay, anyway, so let's look at this one here. Look at this molecule here. How many different types of hydrogen do you have here? 2. And that's what you see here. You only see 2 signals. Okay? You only see 2 signals. And one signal is at about 1 point, is that, let's say 1.2? Okay. Okay. 1.2 parts per million. And this other one is at about what? Which one here? Give me something. Give me a number that makes sense.
3.7.
3.7. Okay, I'll take that. 3.7. And which is the 3.7? Where is the 3.7? Which carbon here? Exactly. So you guys are becoming experts. You see how easy this is. Which is at 1.2? This here. Okay? So what can we do? We could give you this spectrum here, remove this structure, and tell you to give us the structure, right?
How do we know though? How do we know about the other 2 carbons in there?
Which one?
The 2 ones that aren't.
We'll give you the molecular formula. Either we'll give you the molecular formula or the molecular weight. Okay. We might even try to be generous and tell you, I'll give you the IR data. The IR data that has a carbonyl. So all of those pieces you add together. Okay? Now, I told you before that you do integration. In the old days, you see, this was from my old book. We used to do then draw the line to measure the number of hydrogen. Now the instrument will tell you. But the way you do that, you have to, let me show you the next slide. Not that. Where's my integration now? Yes. Huh? Oh no, these are not mine. The color ones are these. No, these are from your book now. No, the ones that are not colored, those are mine. Huh? I'm not cold. I'm not cold. Are you guys cold? Yes. You are? You probably turn the arrow. Okay. Okay, this is what I was trying to get to. See the integration that the way we used to do it, and I would probably wanted to do a couple integration like this. To determine the number of hydrogens given these signals, what we do, this is what we call the integration line. This here. So what you do, you measure you take a ruler, you measure the distance between the base of this here to here. Like in this case, you have 19 millimeters. You do the same thing here, then you do the same thing here. Then you divide by the lowest value, which is what I have here. You divide by this, so that gives you 2.5, 1, and 1.46. Okay? Because you cannot have 1/2 of an atom, you multiply this value so that you get an integer, a whole number. Integer. Okay? So you get an you get the whole number, you multiply by an integer to get the whole number, and that is essentially what this is saying. Now let's see, where is that? Okay, so you get this here, 5, hydrogen, 2 hydrogen, and this here, and that's molecule right here. So that's how you used to do that. So anyway, we have almost finished our discussion of NMR spectroscopy, no, proton NMR spectroscopy. I want us to do a couple of problems before we go. Do you have time? Oh, we have time. You got time? Okay. Okay, now, ordinarily I will start with carbon 13, but I will save that till next Tuesday. But let's do some problems. These are all carbon 13, we come back to that. Come back to that. Or do you want us to start carbon 13 now? No. You want us? No. Oh, okay. Okay, I say congratulations, but we are not there yet. We have not done carbon 13 yet, so let's do, okay, let's do this problem. Okay, let's go ahead and read this question first.
Provide a structure for the molecule with the NMR spectrum below. The MS molecular ion is at NZ74.
Okay, very good. Remember, Emma, you asked why do we know why do you care whether it's a quartet? Oh. Okay, now let us provide a structure for this. This is what you have. When you have a problem like this, the first thing I will do, take the value that you have in this graph, take convert to this tabular form. Okay, so let us give the data in tabular form. Okay, this peak here, what is the chemical shift here? Right here. About 1 point. No, just give me some close number. 1.2. Okay, 1.2. See what they've done? They expanded that signal for you. Because it is a triplet. So 1.2. So they're giving you 1.2. So what you do to convert to the tabular from 1.2, what is the multiplicity? It's triplet. Okay? I will tell you now. Yes.
How is that? Oh, that's a triplet because it's seeing those three.
Yes. Because it is a triplet, okay? I will tell you now in terms of the multiplicity. Okay? Right.
Oh! Okay. I'm not going to come up here.
Keep in mind the molecular weight we have here. We have a molecular weight of 74. Okay? So now we have a triplet, and remember this one here, before we do the number of hydrogen. We also have this peak here. What is the chemical shift here? What is it? 3.5. Exactly, 3.5. What is the multiplicity? Quartet, okay? Okay, let me ask you this. When you see a triplet and a quartet, what does that tell you? It tells you that a CH3 is next to a CH2. Right away, once you see that, that's a giveaway. So, you see a quartet and a triplet. What that tells you is that you have a CH3 next to a CH2. Is that clear? You see that? This molecule only has 2 signals. Right? So what does that tell you? You have a molecular weight of 74. It's a symmetrical molecule. Whatever is on this side must be on that side. You see that? You see how simple this is? So what would be the structure of this molecule? Supposing that then, therefore saying, well, it's possible that I have CH2 here. Alright? Okay, let's add those together. CH2 plus CH3, that's 29 times 2. And what is that? 58, right? Okay, the molecular weight is 74, right? 74 minus 58, what does that give you? 15. So what does that tell you? There's oxygen between them. Right? You see how easy that is? Yes.
I don't get how you know it's the metric level.
Okay. You have a molecule that has molecular weight of 74. At this point, you only see two sets of signals. So in other words, it has only two sets of hydrogen. Okay? If it has two sets of hydrogen, and those two sets of hydrogen is only a CH3 and a CH2, okay? There's no way a CH3 and a CH2 will add up to 74. So in other words, there are some other part of this molecule that we are not seeing.
Right. How do you know it's not like other
Like what?
I don't know.
whatever it is does not contain hydrogen. Okay? If you got to come out with something that is logical. I mean, you could fantasize and say whatever it could be, but it's got to be logical. Yes, it's there.
So on the diagram, does the line in between the triplet and the quartet represent oxygen? Or is it just...
Okay, this here, this is your integration line, right here. Right? Okay, if you look at that ratio, it's a ratio of 2 to 3. Really, that's what it gives you. It's a ratio of 2 to 3 or 4 to 6. If you measure this distance here, from here to here, and the distance from here to here, that ratio is a ratio of 6 to 4 or 2 to 3. Okay, and that is telling you the number of hydrogens. See, most of the instruments today will tell you right away the number of hydrogen without giving you having to worry about integration line. But in case you are not given the number of hydrogen, you should be able to determine the number of hydrogen based on the integration line. Keep in mind, the integration line gives you the ratio of the hydrogen. If it is a ratio of 2 to 3, 2 to 3 is the same thing as 4 to 6. Okay? So anyway, so we solved that problem, right? Okay, let's go to the next one. Yes.
With the 3.5 ppm, did that tell us that there is bouncing oxygen?
Exactly. You see, the 3.5 ppm also tells you it's next to something, the oxygen or something that is electronegative. So the chemical sheet tells you something also. Okay? Okay, let's see if we can do one more before we go.
In 1 minute?
In one, let's see. Okay, let's do, this one is easy. Here, they're giving you the molecular formulas. C5, H10, and 1 oxygen. Now, if you do the index of hydrogen deficiency here, I know you've forgotten about that, right? It's 1, right? The index of hydrogen deficiency is 1. So it's either as a ring or a double bond. If you look at this, triplet, so we have, okay, let's start with this. We only have 3 signals here. Okay, that signal is 0.9. Okay, and the multiplicity is triplet, and we'll come back to the number of hydrogen later. This one here, right here, that's about 1.5, okay? Multiplicity, let's call that multiplex. Okay, it's too many to be worrying about that at this point. Okay, but if you look at it though, we could count it. 1, 2, 3, 4, 5, 6. Okay? That is in 5 equivalent, so let's call that multiplex. There is something called multiplex. Okay, when it's more than, anything more than 4, sometimes we refer to as multiplex. Okay, then we have a peak at here. right here, that's about 2.2. Oh, and that's a singlet. This one here. That's a singlet. This is the triplet here. This is the triplet right here. That is for this. You see that? This here is a singlet, which is at about 2.2 singlet, and then the last thing we see here is this one at about 2.4, and that's a triplet. Okay? And that is a triplet. So therefore, we have...
Oh, so that big one right there is 2.2.
Exactly. Okay, keep in mind the formula that we have here is this.
That one at 3.
Which one is? No, this is this one here. Is this one here? They just expanded it. Which big one?
Yeah, she's saying the big one is that.
This one here is this.
The big one is that.
Oh, yeah, that's what I was saying.
That was expanded. Okay? So, okay. So now let us start working. Let's work on this. We are 0.9, so we say we are triplet. This here, CH3, next to a CH2. This would be a triplet right here, 0.9. Okay? And therefore, this one here, okay, this one here will be okay, so you have something here. Another CH2. This will be the multiplet because it is seeing this here and this here. Okay? That will be the multiplet, and that will be what we have. We have 1 point. That is the 1.5. I'm sorry. That is the 1.5. And then this one here, the 2.2, the 2.2 right here, okay, will be next to a carbonyl because we have oxygen here. Keep in mind we have index of hydrogen deficiency of 1. Okay, so this will be, that is a triplet. Let me get this back here. That is the triplet here, so that's 2.4. That is triplet. And finally, we have a singlet, which is this here, which is the one at 2.2. Okay? And if you look at this formula here, it fits this molecular formula that we are given. Anyway, this is the kind of thing we are going to be doing on Monday during the online session. So, and then on Tuesday we'll finish up the NMR spectroscopy when we do the contacting NMR. So you guys enjoy your weekend.